Welcome back. Last time we looked at the atom, we used a straightforward rule for placing electrons. You fill the inner layers first and then move to the outside. This diagram shows a potassium atom with 19 electrons. Following that inside-out rule, the first two layers fill up, leaving a configuration of 2, 8, and a final 9 in the third layer. But in reality, the layout is 2, 8, 8, 1. That final electron leaves the third layer partially empty and jumps out to a new fourth layer. To understand why that electron moved, we have to adjust how we picture the atom itself. Up until now, we've treated an electron shell like a single, wide-open space. The way these layers are built internally explains why that electron behaved the way it did. If you zoom in on an electron shell, you find it works a lot like a floor in an apartment building. Instead of one large room, the floor is divided into separate apartments of different sizes. We call these apartments subshells, S, P, D, and F, each with strict limits. The S holds 2 electrons, P holds 6, D holds 10, and F holds 14. Moving outward, each new shell adds a room type, until the fourth has all 4. This structure introduces a specific rule for electron behavior. An electron doesn't automatically look for the shell physically closest to the nucleus. Instead, it looks for the location with the lowest energy cost. Since these subshells require different amounts of energy, physical distance from the center isn't the only thing that decides where an electron settles down. Think of a hotel where a basic room on the 4th floor is actually cheaper than a luxury suite down on the 3rd floor. An electron acts like a thrifty traveler carrying a heavy suitcase. If walking up an extra flight of stairs saves them money, they will take the stairs every time. Now apply that logic to potassium's 19th electron. After the first 18 electrons fill the configuration of 2, 8, and 8, that final electron faces a choice. It can go into the complex D subshell on the 3rd layer or the basic S subshell on the 4th layer. Even though the S subshell on the 4th layer is further from the nucleus, it costs less energy than the D subshell on the 3rd. The electron chooses the cheaper S subshell, which results in that final configuration of 2, 8, 8, 1. Our original inside-out rule just needed a bit more detail. Once we see internal energy prices, the exceptions in the science reveal themselves as logical choices. The connection between these subshells and the numbers from our first lesson becomes clear when we look at the total number of electrons each layer can hold. Look at the math for each floor. Layer 1 has an S subshell totaling 2. Layer 2 adds P, so 2 plus 6 equals 8. Layer 3 adds D, totaling 18. And Layer 4 has all of them, which totals 32. The numbers 2, 8, 18, and 32 weren't a random list to memorize. They were simply the sum of the subshells all along. There is one final way to see this architecture in action, and it involves the uneven shape of the periodic table. Notice the widths. The left block is 2 columns wide, the right is 6, the middle is 10, and the bottom rows are 14 columns. 2, 6, 10, 14. These match the exact capacities of the S, P, D, and F subshells. The periodic table has this shape because it is essentially a floor plan of the atom subshells. The map reflects the actual territory inside the atom. Now that you can navigate the internal address of an electron, you have the tools to understand how it actually moves. Next time, we'll see why the famous image of an electron orbiting a nucleus like a planet is completely wrong. See you then.